We're now on the third video of my introduction to plate tectonics. In this video, I want to talk about the boundaries of the plates and the processes occurring at those boundaries. Let's give it a shot. So up we go to learning goals. The first learning goal is that you need to know something about the geometry of the boundaries, the processes that are occurring there, and the mechanics of different plate tectonic boundaries. You also need to be able to identify on Earth where examples of different boundaries lie, and you need to understand something about the forces that are driving the plates and the role of water and carbon dioxide in facilitating plate tectonics on Earth. Now, under the geometry processes and mechanics, a major point is that every student should be able to draw a cross-section through convergent and divergent plate boundaries, and you should be able to illustrate the layers, the compositional layers, as well as mechanical layers, the processes and the mechanical steps that occur, and you should be able to identify appropriate thicknesses of all layers. You need to explain why the features behave as you illustrate them on these cross-sections, and you need to know the difference between compositional layering and mechanical layering. So let's look first at divergent boundaries. I start with this picture in terms of composition. So we have the mantle. Now, the mantle in regions where upwelling occurs is going to be hotter than the surrounding mantle. Because the mantle is hotter, it's less dense, it will rise higher than the surrounding mantle on either side. That's simply a process of isostatic equilibrium. Now, since the mantle is hot there, it is being transported horizontally. The next thing that happens is that hot mantle moves away from the point at which it first arose, and as it moves away, it's sitting at the Earth's surface longer, it will cool off, get denser, and sink. So the mantle that is near the Earth's surface but has been displaced away from the midpoint is sinking down. The overall result is to form a topographic high, a ridge. This mid-ocean spreading ridge then reflects isostatic equilibrium of the mantle at the Earth's surface. It is high in the middle because the upwelling is delivering hot materials. It is lower as you progress away from the ridge because the material has been near the Earth's surface longer, cooled and densified and subsided. Also going on at the ridge is partial melt as the upwelling pressure releases parts of the mantle. That pressure release of the mantle leads to a little bit of melt, less than 10%. That 10% melt, the basaltic magma, comes up at the ridge crest, at the spreading center, and forms the crust. The crust is basaltic, forms right at the spreading center, and then is carried passively away from the spreading center by the continual movement of the plate. Now, the composition of the material being made right at the oceanic spreading centers is distinct from other kinds of basalt. It's called mid-ocean ridge basalt, or MORB, M-O-R-B. As the material moves away from the spreading center, it's sitting at the ocean floor for increasingly long periods of time. It collects detritus settling out of the ocean. The sediment thickens as you move away from the ridge. And the yellow layer there represents a thickening sediment with distance or age away from the spreading ridge. Spreading centers are the most volcanically active place on Earth's surface. They are almost continuously active, and they stretch around the entire globe. There's some 64,000 kilometers of spreading ridges on Earth's surface. Let's look at this from a mechanical perspective, and I've again drawn a cross-section, but now mantle is replaced by asthenosphere. So there, see, it says mantle, now it says asthenosphere. The asthenosphere in the upwelling region is buoyant and rises. There's our mid-ocean spreading ridge again, And you notice in this drawing, I've given some scale. It's about 2 to 3 kilometers higher than the surrounding ocean abysses. As the material moves away from the ridge, it cools off. So in time and distance, the ocean gets deeper away from the spreading ridge. Why is that? Again, I keep emphasizing progressive contraction, denser rock mean deeper oceans. Now that denser rock, the part of the mantle that has cooled off as a result of being near the Earth's surface, is what we call the lithosphere. The lithosphere starts out at 0 thickness at the mid-ocean spreading ridge and gets progressively thicker as you move away from the spreading ridge. It is colder, and as a result of being colder, it is more rigid, it is more brittle, and it's denser. There it is, definition of a plate. So the oceanic lithosphere includes both the mantle and a very thin crust. And as I'll point out in a minute, these drawings are never drawn to scale, and they always overemphasize the thickness of the crust relative to the thickness of the lithosphere. So the crust is thin, and because it's so thin, it really is mechanically insignificant. So lithosphere is mostly mantle with just a tiny bit of crust at the very top. So the boundary between the lithosphere and the asthenosphere, again, I emphasize, is not a sharp line as drawn here. It is a gradational region that it occurs around a point at which the rock reaches a temperature of about 1300 degrees centigrade. So at the Earth's surface, the bottom of the ocean is a pretty uniform temperature, close to 0 degrees centigrade. The lithosphere base follows a constant temperature curve. This curve gets deeper and deeper with distance away from the ridge. Older lithosphere is thicker lithosphere. I throw in here some pictures of processes at the mid-ocean ridge. Here is a hydrothermal vent, water circulating down into the cracks at the base of the crust at the ridge, coming back out as a black smoker. Let's see if I can play that again. You can see very active microbial and various kinds of invertebrate creatures living there because of the chemical nutrients provided by the effluent from that hydrothermal system. Now here's underwater eruption of basalt. This is in Hawaii rather than at a mid-ocean ridge, but it's still illustrative of how magma reaches the base of the ocean and can flow out on the ocean floor and produce a set of features we call pillow basalts, these lobate features as the lava pushes out in the water and is instantly chilled and forms a rind and then breaks out to form yet another pillow as more lava backs in behind the original flow. So think of these kinds of eruptions occurring almost continuously on this 64,000 kilometer chain of oceanic spreading centers around the world. Let's look at now the convergent boundaries. So here's our picture at the mid-ocean ridge. Let's just push it off and follow what's going on beyond that. Now, one of the things I do here is I'm rescaling my drawing. So I've taken the ocean water there and I've replotted as a much thinner layer. Why have I done that? Well, we do have the lithosphere. The lithosphere is about 100 kilometers thick, and the oceans are about 5 kilometers thick. So our previous drawings were totally out of scale. Lithosphere did not show its true thickness. If we had, then the ocean water would have been negligible thickness. Even in this drawing, the 5 kilometers of ocean over 100 kilometers of lithosphere, the way it's drawn here is not to scale. We would have to extend the lithosphere out the base of this drawing to get it to scale with that thickness of ocean. So keep in mind the out-of-scale drawings that we always use to illustrate these principles. Now, lithosphere extends across the planet from the upwelling zones. Eventually it gets to where the mantle is downwelling. Let's see, so we have downwelling on this side now. and the lithosphere would follow that downwelling down. Let me step over to the far side here. We have a downwelling lithosphere. Now, so this downwelling region of the lithosphere is what we call the subduction zone. Let's look at the mechanical layers associated with the subduction zone. Well, let's put in a lithosphere that's being impinged on. So here we have a case of two oceanic lithospheres, and one oceanic lithosphere is going down. You'll notice right where it goes down, there is a deeper portion of the ocean. That's the trench. All subduction zones have trenches associated with the bending of the lithosphere to go down. Trenches are the deepest points in the ocean. Marianas Trench is 11 kilometers, so you see a trench is about twice as deep as average ocean depths. Little extra bit here, there's the mantle underneath the overriding plate. It's called the mantle wedge, and it also will be part of the flow regime. It'll be pulled along with that subducting lithosphere going down. Let's see, what have I added now? Oh, right where that's the little red spot, and let's see, it's somewhere in there. That's where melt occurs to make volcanoes of the volcanic arcs of all subduction zones. That point is about 100 kilometers, 125 kilometers below the surface. Volcanoes lie directly above it. Why? Because melt occurs at that point. The melt rises up to make the volcano, which then erupts, as I show there. Okay, so that volcano then would be part of what we call the volcanic arc of subduction complexes. Now, earthquakes occur at all subduction zones, and I'm going to step over to the far side and note that there are earthquakes that occur where the slab begins to bend down into the subduction zone. So as it bends, the lithosphere begins to crack. Now, as the two lithospheres slide side by side, there's a zone called the megathrust zone, where faults are along the interface between the two lithospheric units, and the relative motion is as shown by the arrows. The megathrust earthquake zones around the Earth are where the largest earthquakes on Earth occur. They go up to magnitudes of greater than 9. Below the megathrust zone, there is a zone of earthquakes shown by red going down the slab. These are the interplate earthquakes, or the Wadati-Benioff zone earthquakes. And they define the trend of the downgoing slab into the mantle. They extend to depths as great as 700 kilometers. Only in subduction zones do you see trends of earthquakes going so deep into the Earth. Okay, convergent boundaries. Let's look at some examples. Again, here's our example from Guam in the Western Pacific. We have the Philippine Plate to the west and the Pacific Plate to the east. The Pacific Plate subducts beneath the Philippine Plate along a trend shown in the arc there, and there's a deep trench all around there. The volcanic arc lies behind the trench, following the chain of islands. Now, the cartoon we always draw, and I've reversed it so you see the letters are backward, but cartoon is as shown here, with the downgoing lithosphere diving beneath the oceanic lithosphere on which Guam resides. There are a chain of islands across the ocean as the lithosphere gets to a depth of about 100 kilometers. Notice in this drawing again that the thickness of the crust is out of scale to the thickness of the lithosphere. Lithosphere should be drawn much thicker than that. This is only a schematic illustration of what's going on at the convergent boundary. Let's look at a ocean-continental conversion. Here we have the Nazca Plate moving to the east relative to South America moving to the west. Now, the subduction occurs along the coastline with the Nazca Plate diving under South America. There's a trench throughout that region, and behind the trench there's the Andes Mountain with a whole chain of volcanoes. Here's a cartoon showing that kind of convergence zone. You see the continental region on the right side and the oceanic on the left side. You'll notice again everything is out of scale, although it does show diagrammatically the continents are thicker than the ocean, and perhaps the continents are a little thicker under the mountain range than they are behind the mountain range. And again, it shows as the oceanic plate goes down, it reaches a magic depth where partial melt occurs and magma rises to make the volcanoes. Finally, we go to the continent-continent collision, India against Asia. We have India there, Asia to the north. India moving north under Asia. Originally, there was a convergence zone with subduction occurring under Asia. Now India as a continent, pushed against Asia as a continent, has greatly thickened the crust in that region. It has turned off the subduction and the volcanic action, but it has generated and continues to generate a very high elevated regime. Let's walk through some boundary examples. So if we take a cross-section through the Earth starting at the Andes, we have the Nazca Plate diving underneath South America, forming the Andes as the volcanic arc, having the deep trench along the South American coastline on the west side. That is an ocean-continent collision. Now as we move behind and to the east, we have the mid-ocean spreading ridge, the mid-Atlantic rift, and we have oceanic crust on both sides of the mid-ocean ridge. We have upwelling and movement of South America to the west and Africa to the east. Moving farther along this profile, we come to Africa. And again, there seems to be upwelling under Africa that is generating a rift valley through the Eastern African regime, and that would be a continent-continent divergence area. Continuing on this trend, we come across the Indian Ocean to the Carlsberg ridge system, which again is a mid-ocean ridge, ocean-ocean divergence zone, ocean crust being produced and spread in both directions. Let's take another cut through the Earth, starting at a ocean-ocean convergence zone in Japan, where the Pacific Ocean is diving underneath Japan. Japan is an island arc complex. It has thickened oceanic crust, but not much continental crust. It's an ocean-ocean collision. Again, the volcanic arc as the Pacific Plate dives down, and ocean crust on either side. Now you have to go a long way across the Pacific to the East Pacific Rise, where you have the ocean-ocean divergence, and again the process of mid-ocean spreading with Pacific Plate on one side and Nazca Plate on the other side. Which leads us again to where we started in the Andes with the ocean-continent convergence zone. Now I wanted to bring up a couple other terms. The margin of a continent that has a subduction zone is referred to as the active margin. On the backside of a continent such as South America, you have a passive margin where you have a continent to ocean crust boundary, but you have no active processes occurring there. The active plate boundary is off in the mid-Atlantic. Let's turn to the transform boundaries. There are the ocean transform boundaries. We've actually already mentioned that. Here I have, though, a picture of the Atlantic Ocean with the mid-Atlantic ridge, and I've highlighted the mid-Atlantic ridge itself as it comes across. Now you notice that everywhere there are segments of spreading ridge that are spreading east and west, but these spreading ridges are offset by transform faults. And one example is this large offset here, and I have arrows in black representing material produced at the two spreading centers, and you'll notice as it progresses, they go side by side, but then as they continue on, they go, in fact, in the same direction. So initially, there's transform motion until the material reaches the other ridge, at which point the two sections of crust continue in parallel together. So in this middle section, we have an active transform fault. Beyond the edges of the ridge segments, you have a fossil of a transform fault, which is called a fracture zone. So the fracture zone gives you evidence that there used to be a transform motion, but in the fracture zone regime, there's no longer a difference in motion on either side of the trend. A transform boundary in a continental region looks like this. Here's the San Andreas Fault, just north of Los Angeles. The relative motion is as shown by the arrows. You can see the displaced stream that simply is being carried up in this photograph as the left side moves upwards. So here's a map section of the San Andreas Fault. You see North America on the uphill side and the Pacific Ocean on the bottom. Pacific Ocean relative to North America is side by side along the San Andreas Fault. Another example of a large continental transform boundary is the Anatolia Fault, which runs from Central Asia all the way over into Turkey. Here you have, again, side-by-side motion between an Anatolian small plate and the Eurasian plate to the north. Let's talk about the forces driving the plates. Well, plates are strong and dense. They should organize the convective flow that occurs below them. And there are three major force contributions that we can think of. Number one is something that is called ridge push, and I'll explain that in a minute. Secondly, there's something called slab pull. And finally, there is basal drag. Let me illustrate these by giving you a cross-section from a ridge all the way into far distance from the ridge. So there's the ridge, and there's the lithosphere. Now you notice the lithosphere-asthenosphere boundary forms a surface that is increasing in depth. If I were to place a ball on that surface, it would simply roll down it. Likewise, the rigid lithosphere sitting on top of the ductile asthenosphere can also slide down that interface. The lithosphere is denser, just as that ball was denser than the air around it. So in fact, the lithosphere can slide on the surface provided by the increasing depth of the asthenosphere. This sliding by gravity down the topography of the ridge is what's called ridge push. Now, at the other end of the stick is slab pull. We have the lithosphere, and we stick it down into the mantle in a convergent zone. This material that we're sticking down is colder, it's denser than the surrounding mantle. There is a body force then acting to pull it down deeper in the mantle. This stuff wants to sink because it is hot, colder and denser. That body force then pulling downward is slab pull. So finally we have mantle drag. The first two forces that I talk about are things that would accelerate the flow. Mantle drag is something that would retard the flow. So as the lithosphere moves along the asthenosphere boundary, it is going to pull on the asthenosphere. There will be a resisting force that we call drag. There's drag there, and that drag resistance would keep the lithosphere from accelerating. There's also drag force as the plate is being subducted deeper into the mantle. So overall, there's going to be a balance of forces if things are in steady state. If plates move at a steady rate, and they seem to over very long geologic periods, then all forces need to sum to zero. So the slab pull plus mantle or plus ridge push, both trying to move the plate, is being retarded by mantle drag. So finally, I want to talk about H2O, and I'll just mention CO2 is important too, and suggest that both H2O and CO2 on Earth are the essential components that make Earth a planet of plate tectonics, whereas we don't see plate tectonic structures on either Mars or Venus. So let's talk about how water can change the behavior of the solid Earth. First of all, there's this interesting image here from the USGS, which illustrates just how little water we really have. If we sucked all the water out of all the oceans, out of all the rivers, streams, all the groundwater, it would form a single ball with a radius of about 680 kilometers. And so we've just set that over the mid-US in this image. That's all the water there is on all of Earth. Now that water came from outgassing from the mantle, and that water is being recycled into the mantle by the subduction process. So there's all water. Now the smaller diameter ball, that's about 20, well, I forgot what its diameter is, represents all the fresh water on Earth, and the very tiniest ball, which is only 20 kilometers in diameter, represents all the water that exists in lakes and rivers. The larger freshwater ball, most of that is the ice cap water. Okay, so what does water do? Well, water reduces melting points of rock. You add water, it melts at hundreds of degrees lower temperature. So any place that has water, for instance, a subduction zone pulls the water in hydrous minerals and trapped water in pores back into the Earth. That localizes where melt is generated. Furthermore, water acts as a flux to aid in fractionation of chemicals to make different kinds of crust. So H2O is a reducer of melting temperature and a flux for chemical reaction. Furthermore, H2O has this wonderful ability to weaken rocks. It can change both the ductility of the rock, enhancing ductility, and it can make rocks fail at much lower stresses. So wherever there is water in the rock is essentially weaker. Again, subduction zones are weak because of water. And it may be that on Venus, for example, we don't have subduction processes like Earth simply because there's no way to weaken the rock enough for subduction to start. So not only is water critical for life on this planet, but it seems critical for the basic geologic processes of this planet. I don't have time, and it's beyond the context of this video series, but CO2 is equally important. So that brings an end to my discussion of boundaries and processes. My last video will consider earthquakes, magnetics, and hotspots.